Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over some practice problems for how to calculate the equilibrium constant from your equation and your given information. So let's get into this. First of all, let's remind ourselves what the K expression is, the equilibrium constant expression. So if we have a generic equation, I'll just write it here. So A plus B gives me, or we'll just say we'll have little a times little a of A and little b of B, little c of C plus little d of D there. So the little letters are the coefficients. And so according to the law of mass action, the concentration or pressure is going to affect the equilibrium in some way. So the equilibrium is going to be based on concentrations or pressures or partial pressures of the substances, products and reactants in the equation. So we write the Kp in this way. So Kp is equal to the partial pressure of products. It's going to be products over reactants. So partial pressure of C, big C, raised to the power of C, multiplied by the partial pressure of big D, raised to the power of little d, the coefficients, and then all over the partial pressures of your reactants. So it's going to be the partial pressure of A, big A, raised to the power of little a, the coefficient, multiplied by the partial pressure of big B, raised to the power of little b, its coefficient. And the Kc is the exact same, except the only difference between Kp and Kc is that instead of partial pressures, you're dealing with concentrations. So that's the only difference between your Kp and Kc expression. So here we're given an equation, and we're given the partial pressures of each of the substances, and we're asked to calculate Kp. So then we're going to write out the Kp expression first. So Kp is going to be equal to the partial pressure of this substance here. So it's going to be the partial pressure of C2H5OH. And that's the only product. And that's going to be over the divided by the partial pressures of these two. So it's going to be the partial pressure of C2H4. Okay, C2H4 multiplied by the partial pressure of H2O. Oops, I forgot partial pressure. So P H2O. And so here, let me double check. Let me make sure I got my equation balanced correctly. Okay, so we have 6 over here, 6 over there, 6 hydrogens, 2 carbons, and 1 oxygen. Okay, so it's balanced. So notice that the coefficients here are all 1. So the powers, they're all raised to the power of the coefficient, which is 1. So these are all raised to the power of 1, but we don't write the 1s in. Okay, so now all we need to do is plug in the partial pressures that were given us. So the partial pressure of C2H5OH is 0.11, right? And then the partial pressure of C2H4 is going to be 0.35, so 0.35. And that's going to be multiplied by the partial pressure of water, which is 0.75, 0.75. And now I'm ready to calculate. Now, before I calculate, I want to point out, you might notice that I'm not putting the units of atmosphere into my equation. The reason is because technically there are no units, because we're taking the atmosphere and we're multiplying or dividing the atmospheres we're given by one atmosphere, because that's the standard. And so really this would be 0.75 atmospheres divided by one atmosphere. So therefore it's just 0.75. This would be 0.35 atmospheres divided by one atmosphere. So it turns out to be 0.35 and so on. So this is a unitless constant. Even though it may seem like we should have units in there, it's not. There's no units. Okay, so now we're going to calculate. And when we calculate the answer, we get 0.419. So 0.419. And again, going to sig figs, for those of you interested in sig figs, remember the rule: when you're multiplying and divide, the answer should have the same number of sig figs as the measure with the least number of sig figs. So this has 2 sig figs, this has 2 sig figs, this has 2 sig figs, least number is 2. So that means we should limit this to 2 sig figs. So we have 1, 2, and then we drop the 9. So we need to round this to 0.42. So that is the equilibrium constant for this reaction with these partial pressures. And again, unless you change the temperature, this is always going to be the constant. The constant doesn't change, hence the name constant, when you change the partial pressures. So I can change the partial pressures, and it should, if the equilibrium is constant, I should always get the same constant here, right? So if I add some of this, it'll equilibrate again, so that the partial pressures are going to be different, but the partial pressures at equilibrium, whatever they are, should give me the same number, 0.42. Okay, let's go ahead and do the next one. So here we have this equilibrium equation. We're going to write the expression. So again, we're going to have Kp is equal to the partial pressure of CH3OH, methanol. So that's going to be the partial pressure of CH3OH on top, and then we're going to have the partial pressure of CO on the bottom. So partial pressure of CO multiplied by the partial pressure of H2. And notice that we have a 1 coefficient here, so this is raised to the power of 1. We don't write the ones. Again, same for CO, raised to the power of 1. Now for hydrogen, it's raised to the power of 2 because we have a 2 coefficient. So we're going to raise that up to the power of 2. And so now all we need to do is plug in the values that we got from our problem. So CO is going to be 0.96. The CH3OH is going to be 0.11. So let's put in 0.11. And then then the CO is going to be 0.96. So 0.96. Again, I'm not writing the atmospheres because those are already canceled out. And then 1.92. So this is going to be 1.92, and it's squared. And so again, we're going to calculate the answer. And when we do, we get 0.031. So 0.031. And again, we have 2 sig figs here because this is 2 sig figs, this is 2 sig figs, this is 3. So the smallest number of sig figs is 2. So we limit our answer to 2 sig figs. And once again, this is the equilibrium constant for this reaction. So if I was to change the concentrations, if I was to throw in some more methanol or change the amount of H2, the equilibrium would reestablish with new concentrations, new pressures. And so therefore, when I plug those new values into the K expression, I should get the exact same answer, unless, of course, temperature changes. If temperature changes, then the equilibrium constant will change. But barring any temperature changes, you should get the same value each and every time. So that's it for this video. If you enjoyed this video, then please like the video, share the video. I hope you learned a lot from this video. If you did, then please subscribe to my channel and make sure you click the notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. I would love to hear from you. Let me know what you think. Ask me questions. If you got a question or a problem you want me to go over, let me know below. If you've got a topic you want me to cover, let me know below. I would love to do that for you. Thanks for joining me and have a great day.